Hi there, my name is Scott and I'm going to be talking to you right now about using deep learning to analyze steganography, essentially perform steganalysis. So what steganalysis is the process of taking an image like, say, this nice lake with its trees and sky and hiding some secret message in it by maybe, say, changing the pixel data or the metadata in a way that, someone else could retrieve it later. Now, the thing that steganography has over other methods like encryption is the fact that with steganography, there's no, I suppose, paper trail. There's no real evidence that there is something to be hidden unless people are specifically looking for it. In the case of encryption, when you see an encrypted file, everyone's first instinct is that there's something important hidden behind it. That's just how it goes. So I've already taken the liberty of downloading our fun tree and water picture off the internet, cropping it and converting it to a PNG for our uses, and encoding a secret message in it. And as you can see, the two images, the cover and this stego, are pretty much identical. Like, if you looked at both of them, you can't really tell the difference. But if we run it through our steganography library, code, we see this string of letters, which I generated randomly and encoded it with before making this video. Now the big question is, can we use software to analyze whether or not a secret message was hidden? And the answer is yes, that's what steganalysis is. But those techniques are typically very difficult and kind of time consuming, and there's a certain problem with the fact that there are so many different encoding methods that it's kind of an enormous pain to look for all of them using all these different kinds of software and like every possible image you could ever look at. It's just too much work. Neural networks have this great benefit in that once you finish training them, they're incredibly fast. And so what we can do now is, this is the Jupyter notebook in which we have our neural network trained. Now, a neural network is essentially a trainable AI, I guess. It's difficult to describe, but the point is they can be trained given large amounts of data to be good at a task. And for this, I actually used 60,000 images to train the neural network. It took up 20 gigabytes and several days of training. The training process is pretty time and resource intensive, but once you have it, a neural network is typically very small, a neural network is typically very fast, and those gains are pretty important. So now let's have our neural network look at our cover nature image. Now the number that it output right here, this negative 0.4567, represents whether or not it thinks that the image is hiding some secret message. A negative number indicates that, no, I don't think it's hiding something, and I'm about 45% confidence, if you want to think about it that way. Now let's try putting in our stego image. And what we get is a much, much higher value because there is data hidden inside of it. The neural network has learned that there is information there to be had. It doesn't necessarily decode it, but just knowing that it's there tells you that there's something, gives you better direction to look for something. Now, it's important to keep in mind several things. This neural network is trained on this specific encoding method using this specific steganography package, and it's not really advisable to train a single neural network to identify every single kind of encoding technique. If you wanted to train it on a different encoding technique, I recommend that you would initialize a new neural network using this class, which defines the convolutional neural network structure, and training it with your own data set encoded with whichever encoding method you're interested in finding. Again, because neural networks are very lightweight, you have this great benefit of being able to use many of them at the same time, and you saw for yourself just how fast that was. Now, for those of you who have experience with neural networks, you might know that a neural network requires you to have inputs of a fixed size. In this case, the neural network only tolerates inputs of 256 by 256 pixels in color, RGB, three color channels. So we need to have a way to deal with larger images because no images in life are really that size. And so what we do is, instead of trying to scale it down because that causes corruption in the data that's probably being hidden, we actually do the similar technique. We take the large image and we chunk it into smaller pieces. And if any of those smaller pieces look like they might have data hidden in them, then the system will say, hey, I think that data is hidden here. The thing about steganography is that it doesn't necessarily modify the entire image, it only modifies parts of it, and so it's not really a good idea to take a general average, because a lot of it is going to be unmodified. Just to give you kind of a feel for how different the two images are, again, even though you can't really see it with the naked eye, there is definitely some differences in the pixel data, as can be seen here. These like pink strips represent where the data is different. Now let's try taking a slightly larger version. So instead of 256 by 256, let's crop it to 512 by 512. That seems fine. We'll encode it again with a random string. It takes a little bit of time, but it's pretty fast still. Now, there is this other problem with the amount of data that's been encoded in an image. If the amount of data that you encode is very, very low, like if it's a single letter, then what's going to end up happening is that only one pixel between the two images is going to be different. And so your neural network is just going to write that off as noise, but so will every other technique, frankly. Without having access to the cover image, you're not going to find a single pixel difference in a stego image. It's just not going to happen. So now we have our larger images. Let's take a look at what it thinks. And you see it's still pretty not confident about whether or not it's hiding information. Now with our stego, it's also not confident, but does think that there's something there. Again, the density of data within the image matters very, very much when you do this sort of thing. And since we've basically quadrupled the size of our picture with the same amount of data, it's going to be that much harder to find it. And you can see, if we put this in here, it's just much sparser, the differences. It's going to be much harder for the neural network to find. So if you want to train your own, what you're going to need to do is to get a ton of images. A link is provided with a set of cover images that you can use. A steganography algorithm or a set of stego images, and you're going to essentially label your cover images as, say, -1 and your stego images as 1, and basically your neural network is going to learn, oh, these images correspond to a negative value and these images correspond to a positive value, and that's how it's going to learn. The techniques, the network architecture, the coding of it all is all attached in the zip file or whatever code files that come with this video. I would highly recommend that you use the Jupyter notebook file just because that is what I use to write it, and the Python is just an adapted version of that. If you do use the Python one, it's just a set of methods, so you're going to want to import it in a different set of Python code or in a conda environment. And yeah, that's just about it. Thanks for listening, and